All right. So, what we are doing in this chapter is we're going to start to look at some more detail with regards to the concepts of heat and temperature. We're going to start looking at things that happen on a microscopic level. We're going to start to explore the concepts of pressure and volume and temperature. We're going to go over ideal gas law today. By the end of the lecture, we're going to be able to create a really interesting relationship between the concepts of um, kinetic energy and temperature, how those things are related, because that's what we define temperature as in the first lecture, I suppose. And we said that temperature is sort of an average of kinetic energy of particles in a system. So we'll do a little bit of a derivation today, and we'll see how that actually looks. Okay, though, now to do a lot of the concepts here, we're going to do a lot of things with chemical elements, and that means we have to deal with moles a lot. And so I want to go over a little bit about that. If you've had chemistry, a lot of this will be familiar to you, but let's go through it. Now, in an atom, the amount of mass that an atom has is almost entirely determined by its nucleus. Yes, electrons have mass, but it's extremely small. It's less than a thousandth of the proton's mass, and protons and neutrons are effectively the same mass. And so to determine the mass of a particular atom, we look here at the atomic mass unit, which is given by this lowercase u here. And you simply need to add up the number of protons and neutrons in a given atom and multiply it by the atomic mass number, and that would tell you how much mass in, say, kilograms a particular atom has. Now, the atomic mass is sort of the theoretical mass of that atom. It's not the mass number. The mass number is something that shows up in the periodic table, and the mass number is sort of an average. It's a weighted average of the relative chemical abundances of the different isotopes, and which is more realistic, because if you say you have a sample of carbon, for example, well, carbon's not a great example because carbon's mass is like almost spot on 12. But if I were to look up, say, I don't know, iron or something like that, right? So we're going to look up iron here. Ooh. So the mass number for iron is 55.845. And so, it's not an exact, it's not a whole number. It's because they take into account the elemental abundances of iron. There's different isotopes, right? But anyway, but for the purposes of doing a lot of things in this class, if we just talk about a sample of iron, we're going to refer to the mass number. And the mass number is going to give us how many grams there are in a certain in 1 mole of a substance. So we deal with moles quite a bit because we're very interested in number of molecules and how that relates to mass. So the definition of the mole is Avogadro's number. So it's 6.02 times 10 to the 23rd something. All right, something. I mean, I could have a mole of pencils, right? I got one pencil here. But if somehow I had 6.02 times 10 to the 23rd pencils, well, I would have a mole of pencils, which would be pretty gnarly, actually. So anyway, if you want to determine the number of moles in a particular substance, you can do that by calculating how many molecules you have in something and dividing it by Avogadro's number. Okay, so for example, well, we'll do examples. How about that? We'll do examples. You'll see how this works as we move along. All right, the molar mass of a substance is it's the amount of mass that's in a mole of a particular substance, and that is given by mass numbers. Okay, so that's units of grams per mole. Okay, now that's what the periodic table is going to give you when you look up molar masses of things, grams per mole. However, be careful about that because we don't typically use grams in calculations. It's not strictly SI. So when we have concepts of pressure and things like that, you're going to have to make sure to remember to use kilograms when you're doing things, doing calculations for things. Okay. Now, the number of moles in a substance can be determined by the amount of mass, which is just lowercase m, divided by molar mass. Again, the grams per mole, and that would tell you how many moles. So if you have, for example, 18 grams of water, you have 63 grams of water, and the molar mass of water is 18 grams per mole, and we get that just by adding up the mass numbers there. Oxygen is almost spot on and to be 16, and two hydrogens are 2, so it's 18 grams per mole. So dividing the 63 by 18, we get 3.5 moles of water. Then you can multiply that by Avogadro's number, and you get number of water molecules. So, good. That's basically right. There's some deuterium going on in there, but that wouldn't change. It wouldn't change this number by very much because the amount of deuterium in water, if you are curious, which I'm sure you are not curious, but still, because I'm curious myself, deuterium abundance, it's like 1 in 10,000, I think, something like that. Yeah, like 1 in every 3,300 water molecules can contain a deuterium. Well, that's less than 1 part in 1,000, so that doesn't really throw off this calculation much at all. But it's something, I don't know, I just thought of it. Deuterated water, they call it. All right, so question for you here. Which contains more molecules, a mole of hydrogen gas or a mole of oxygen? Letter in the chat. Let me know what you think. A lot of C's, a lot of C's. All right. You're saying you can't fool me, McGovern. You can't fool me. Which weighs more, a pound of rocks, right, or a pound of whatever? Pencils, Yep, same number of molecules. The molar mass of oxygen is larger, so the amount of mass that you would have would be different, but you still have the same number of molecules. All right, great. So let's do a problem here. How many moles of oxygen is in 100 grams of oxygen gas? And then how many molecules are there? All right, so there's a couple ways to go about this. I mean, there's one really easy way, but I kind of want to illustrate both of the ways to do it. So let's check it out. Now, if you were not aware, oxygen is diatomic. And, throughout the thermodynamics in this class, this is something you're going to want to know. We'll bring this up quite a bit. But yeah, nitrogen, atmospheric oxygen, these are diatomic. So the molar mass of oxygen gas is 32 grams per mole. And so a really straightforward way to do this is to take the total mass of your oxygen divided by the molar mass. So we get 100 divided by 32, and we get about 3.13 moles. Okay. I went with 3 sig figs for some reason. I don't know why. Probably want to go with 2 here, but whatever. All right, that would be fair. It would still be 3.13, actually. All right, now, the other way to do this is to look at what the atomic mass of oxygen is. Okay? So oxygen, it's 8 and 8. 8 protons, 8 neutrons. You got 2 of them, though, so you got an atomic mass of 32. Multiply that by how much an atomic mass is. 5.31 times 10 to the minus 26 kilograms. So that's for one molecule, right? One molecule contains 5.31 times 10 to the 26 kilograms. So if you want to get the number of molecules, you'll have to do the whole, right, divided by a single increment. And so again, you got to put this in kilograms here, 0.1 kilograms, divided by the mass we determined before, and we get 1.88 times 10 to the 24 molecules. Okay, we compare that to Avogadro's number, and we also get 3.13. Okay, now the one on the right-hand side here may have been a little long-winded. I just wanted to show you a different perspective because, we got the moles in the first part here, and then, of course, if you want to figure out how many molecules there are, you just take the moles and multiply them by Avogadro's number, and you'll get the same 1.88 times 10 to the 24 molecules. Anyway, this is a more long-winded way on the right here, but one involved molar mass, one just had you look at individual, protons and neutrons in there, but that's what we're looking to do there. All right, let's push on here. All right, now we're going to spend a good amount of time in thermodynamics talking about gases. And the reason why we do that is because gases, more than any other form of matter, behaves well. Put it that way, behaves well. We can create very simple models of gas, and we can understand a lot of the principles in thermodynamics by strictly sticking with gas. Liquids and solids are a bit more complicated. The reason why they're complicated is because one of the major factors in how a liquid or a solid behaves is that there are interactions between individual molecules. Like there's attractive forces that occur between molecules because of the state of the matter. And that's an extra factor that's very difficult to incorporate. So for gases, we can ignore a lot of these things, and a lot of the predictions that we have will match reality. The other form of matter that we can do is plasmas, but that's a nightmare. Plasmas are a total nightmare because, they're ionized. So it's just a lot of E&M and not easy to model at all. In fact, a lot of solids and liquids are modeled with statistical mechanics, which makes a lot of simplifications, and it's just a lot more complicated to do. All right, so in our ideal gas here, we're going to model all of our molecules as being little spheres. The spheres will float around. They're going to have large spaces between them, so the gas will be considerably sparse. And when interactions take place, we are going to assume that perfectly elastic collisions are occurring, so that energy isn't lost somehow in the collision. So momentum is always going to be conserved. Energy is always going to be conserved when there's collisions taking place, not only with molecules in our system, but with the walls of the container as well. And we're going to make sure that our gas is not in any risk of turning into a liquid or a solid. So that's what it says here about being above the condensation point. We just want to make sure we're not going to deal with that stuff. All right, so we have a couple different forms of the ideal gas law that we're going to work with. The first one here is probably the one that maybe you're most familiar with, because this is the one that pops up in chemistry a lot. PV equals nRT. P is the pressure in Pascal. So that's newtons per square meter. Volume is given in cubic meters. Okay, so if you have other units like liters, milliliters, whatever, you want to make sure you're doing SI stuff here. Okay, the N is given in moles. The R is a constant, 8.31 joules per mole per Kelvin, and the temperature has to be Kelvin. Has to be Kelvin. There's no delta T here, so that means you cannot use Celsius. Can't use Celsius. Don't try it. You may be tempted to. You may screw it up a few times, to be honest, but don't do it. Okay. The other version of this changes the number of moles here, and it really depends on what you have to work with here. But there's a relationship here, and it looks like this. If I annotate this, the NR is equal to capital N times this constant KB. Now KB, I can't really draw a lowercase b there, but the N is number of molecules. So there's a conversion going on here to convert the number of moles into molecules. And, that's simply done by, you can divide these numbers here. You divide R by Avogadro's number, right? It's 2 to the 23rd, and we end up with this number right here. This is the Boltzmann constant. That's just the universal gas constant divided by Avogadro's number, and that's in joules per Kelvin. So this is a different version of the ideal gas law if you happen to have more information about molecules as opposed to moles. Also, the Boltzmann constant here shows up a lot more in physics-related concepts. So we're going to jump back and forth between them, but just to be clear, that's what the relationship between the two are. Okay. So this one up here, well, we'll do some derivation today. I'll just put it that way. All right. Let's move on. Let me clear this out. Right, if the volume of a sealed container of gas is decreased, what will happen to the gas temperature? So, this is a ideal gas law thing. So here's what we're doing. Volume of a sealed container of gas is decreased. What's happened to the gas temperature? Put a letter in the chat and we'll talk about it. What's going on? Where'd my mouse go? Oh, no. There's a missing mouse out here. Okay, I got it. A lot of C's. A lot of C's. Almost everybody's saying C. Well, everybody. Sorry to disappoint you, but it's not C. It is D. Now, there's a couple of reasons why I'm doing this. There's a lot of factors that go in the ideal gas law. If you're trying to look for simple relationships between quantities, you need to know a lot of other factors involved. Okay? And because of that, a lot of times we're going to be using language that specifies different thermodynamic processes. For example, we could talk about an isothermic process. That's one where the temperature is kept constant. We have an isobaric process where pressure is kept constant. We have an isochoric process where volume is kept constant. We have adiabatic processes where the amount of heat or internal energy stays at a constant. So with this thing here, we don't really know what's happened with the pressure. That's the problem. Now the container is sealed, so we do know that the number of moles is not changing. But if we're not told that we have an isobaric process, we don't really know what's going on. Okay? If we knew we had an isobaric process, then the answer would be C. But we just got to be very careful, and this is a warning to just really be mindful of when a process takes place, exactly what things are supposed to be changing and what are not. And we have a whole lecture on this. Where we go over the different processes and stuff. All right, moving on. All right, two identical cylinders, A and B, contain the same type of gas at the same pressure. Ooh, all right. Cylinder A has twice as much gas as cylinder B. So what is going to be true here? What's going to be true? lot of A's, a couple C's. The answer is A. The answer is A. So what do we know here? We know the pressure doesn't change. Okay? We know the volume doesn't change. Identical cylinders. We know we have a greater amount of gas, so the number of moles is up. The number of moles is up. The temperature must be down. All right? So there's an inverse relationship there. Cylinder A, twice as much gas as cylinder B. What is true? All right. Yep. All right. Great. So, yeah. So that's just the mathematical explanation of it. Okay. Now, when you look at this, though, you might be like, I don't know, man. You got more gas in there. Is it really going to be cooler? Well, yes, because you have a constant pressure process. That's why. If you normally just shove twice as much gas in the container, are you going to generally have the same pressure? You generally won't have the same pressure. There's got to be something special going on with this to make the pressure lower here. But that's a separate thing. So you got to kind of be mindful of, are we doing a mathematical thing here or a practical thing? Because tell you what, this is not practical. Trying to add twice as much gas to a cylinder and not increase the pressure, I mean, you'd have to lower the temperature. That's it. I mean, you kind of have to force the temperature down, right? You have to cool this thing down, and then you can have the same pressure, though. So that's probably how practically this would work. It's not like you can just throw the stuff in there and then just magically it cools off. No. Not likely. And when I say not likely, I mean no way. All right. I'm just throwing questions at you, people. Ideal gas law is a lot of concept and a lot of math, so let's do it again. Two cylinders, A and B, contain the same type of gas, the same pressure. Cylinder A is twice the volume of cylinder B and contains half as many molecules as cylinder B. What's true here? Now we got a little bit more going on with this. Oh, I see what you're doing there. T's, a couple C's in here. Well, let's go through it. The answer is D. D. Why? Well, there's an inverse relationship with volume. So if you're doubling your volume, pressure is going to drop by half. And then we know what's going on with the molecules. We have half as many. And there's a direct relationship with pressure, so that means that's going to go down by a half. And the temperature doesn't change, and the laws of physics are not changing, so KB is the same. We may have problems where we go to a different universe and have to solve physics problems. That will be later in the class. I'm just joking. No, it's not. Anyway, so 2 factors of 2. Okay? Both are contributing to making the pressure lower. Fantastic. Let's do some problems. Let's do some problems. All right. We got 100 grams of oxygen gas. Oh, I was a little lazy there. 100 grams of oxygen gas. Well, I chose that because guess what? We already know how many moles that is, right? 3.13. 3.13 moles of oxygen gas is distilled into an evacuative chamber. Evacuated 600 cubic centimeter container. What is the gas pressure at a temperature of 150 Celsius? Okay, so this is a straightforward problem, except for the fact that you got to be really mindful of your units here. So I want to get pressure, right? So I got nRT over V. I think I want to do that version of it just because I already knew the moles. I can do the capital N KB thing too, but I'm going to do this. So I got my moles from the last problem. Got it. R. I already know that. 8.31. My temperature. It's not 150. Right? It's not 150. Don't use the Celsius. Got to use the kelvins. Always do kelvins here. So 150 plus, it's 273. That's the conversion from Celsius to Kelvin. There's a 0.15 on this for sure, but we only got 3 sig figs anyway, it looks like here. So we'll stick with that. Now the volume here, you may not remember this, but if you want to convert centimeters to meters, right, you already know how to do that, right? If you convert centimeters to meters, you're going to divide by 100. But that's when you're converting distances. We're converting volumes. And you have 3 dimensions. So you need to have 3 conversions, 1 for each dimension. So we're actually going to take our 600 cubic centimeters and we're going to divide that by 1 million. Okay, or 10 to the 6th. It's a factor of 100 3 times because we've got a volume thing here. So there actually is a 6.6 times 10 to the minus 4 cubic meters. Now we're good to go. Now we got it. So I put all our numbers in here. Now if you're doing everything SI, you're going to end up with Pascal. That's the standard SI unit for pressure, 1.87 times 10 to the 7. And, a lot of times we use language of atmospheres. So if you want to continue to use that language there, you can divide your pascals by 1.013 times 10 to the 5th. That's the number of atmospheres, okay? And so if you divide that, we get 185 atmospheres, which is pretty darn big. That's pretty darn big, right? Okay, any questions about this? Are we clear about the unit conversions and all that? Let me know. Okay. Okay, let's push on. Push on here. All right. Got an empty aluminum scuba tank that contains 11 liters of air at 21 C and 1 atmosphere. Okay, so that's great. When the tank is filled rapidly from a compressor, the air temperature goes up to 42. The gauge pressure is 2.0 times 10 to the 7. Now, gauge pressure, if you maybe remember from way back in the day, Physics 110, gauge pressure was the pressure minus atmospheric pressure, which would be minuscule here because atmospheric pressure is only like 1 times 10 to the 5th, so it really wouldn't matter if you use it or not. But if you're giving gauge pressure, you want to make sure that that you realize that that's just the pressure in addition to atmospheric pressure. Okay. We want to know what mass of air was added. Okay, so we got all the things here that for the ideal gas law, but we want to know mass of air added. Well, this is a little tricky, right? Because mass doesn't show up in the ideal gas law. The way we get to that is either figuring out number of moles or number of molecules. I like moles. I'm going to go with moles. Now, if we're filling the tank in a compressor, that means the number of moles increased, right? So what you're going to have to do is you're going to have to work a before and after thing here. Let's look at it. A before and after picture here. Okay, beforehand. Now I'm going to rearrange my ideal gas law. So I got pressure and volume divided by RT. We have all that stuff, right? We have atmospheric pressure to start. Okay, so 1 atmosphere is 1.013 times 10 to the 5th. We got to do our volume here. Now, if you weren't aware, now you will be. A liter of gas is 10 to the minus 3 cubic meters. Okay, cubic meters. So, so that's how we're going to do that conversion, because a milliliter is a cubic centimeter. A milliliter is a cubic centimeter. So if you go from liters to get to meters cubed, it's 10 to the minus 3. So this would be 11 times 10 to the minus 3. So if you want to change your liters into cubic meters, it's very simple. You just attach on here a 10 to the minus 3. That's it. Got my R value in here, and then my temperature is going to be 21 plus 273, and I get 0.146 ... moles. All right. Let's do afterwards. I got my higher pressure in here now. I got the same volume, same universe. right? Same, temperature is now a little higher. Now temperature is not doubled here. Okay, this is one thing that people get confused about. 21C and 42C, the temperature did not double. Okay, I mean numerically the numbers doubled, but as you can see here, the temperature went up 21 Kelvin. Well, 21 Kelvin out of, you know, almost 300, it's not even 10% of an increase, actually. So be careful about that. I know it's very common to say, oh, temperature doubled. It didn't double. No, the only time you can say a temperature doubles or halves or anything like that is when you do things in kelvins. Anyway, we get 88.247 moles for the after thing. We're going to subtract those numbers, which I did right here. And then we got to figure out how much mass of air that is. All right, well, that's a little tricky because the air is, 78% diatomic nitrogen and about 21% oxygen. That makes up almost 99% of the air. So I'm going to do a weighted average here. Nitrogen is 28 grams per mole, and oxygen is 32 grams per mole. Okay? So I'm going to multiply, what I'm doing here is this. I'm multiplying each of these numbers by these percentages as decimals, and then add them up, and when you do that, you get 28.56. Okay, so obviously we're in the middle, right? But we're more skewed towards diatomic nitrogen because there's a lot more diatomic nitrogen. That's the easiest way to do that. So again, I just multiplied the decimal equivalents by the molar masses, added them up, and I get the molar mass of air. And at this point now, you can just use this number for any future things. If the word air is used and you have to incorporate mass, you got to work with the molar mass of the air. Okay, so that may not have been clear when you first saw this problem, but guess what? That's why we're taking classes. That's why you're learning stuff, and now you know. If you're dealing with air, you gotta work this out here. Anyway, molar mass of the air times the number of moles. I convert it to kilograms. We get 2.51 kilograms. 2.51 kilograms, which is a good amount. That's a good amount of mass, right? I mean, the tank would feel, that's pretty different because what, like a kilogram is like 2.2 pounds, so we're talking about almost 6 pounds or so here. All right, any questions about this one? It's not an easy problem. I would say this one is not too easy. Anyway, any questions? Yeah. What the heck is that? All right, let's keep going then. Let's keep moving. All right. So, it's very hard to talk about ideal gas law stuff when you can't control the amount of a substance. Like, I can't talk about what's going on outside here using ideal gas laws because, what's your container? What space are you talking about for your volume? Can you ensure that the number of molecules won't change? Not really. So almost all the problems that we do here will be sealed. And if they're not sealed, it'll be very specific that it's not sealed, like the last problem, right? Very specifically, we were told that we have a sealed container and we added mass to it. So a lot of problems involve sealed containers, whether we do add mass or not. If we have a sealed container, we don't increase or decrease the amount of mass, then we can do something interesting mathematically. Because the NR part of the ideal gas law becomes a constant, and then we can now create this proportion. The pressure times volume over T will be locked. That will not change. And so we can create a before and after picture, or equation, I should say, not picture, a before and after proportionality. Okay, so this can help us solve a lot of problems if we manipulate something in a sealed container. And you can do a couple things with this, right? You can look conceptually And if things changes, what are the effects on something else? And it just helps you to solve problems if you know how you change the state of a system. So let me ask you this: the temperature of a rigid, constant volume, right, sealed container of gas increases from 100 to 200 C. The gas pressure will increase by a factor of what? So, sealed container, no mass difference. Isochoric process, constant volume. So all you got to worry about is the relation between pressure and temperature. Now look back here. So if you can cross your volumes out here. You just got a ratio of pressure to volume, of pressure to temperature, pressure to temperature. So think about that for a moment. Put a letter in chat. I'm going to step away for a minute. All right. So glad a lot of you didn't say A. It is not A. It is B. Now, you don't have to actually work out the calculation here because we can see that the temperature does increase. So if the temperature increases according to this proportion here, your temperature goes up, well, the pressure at the end has to be higher. Okay, so we're at A or B. There's no way it could be C or D. Pressure shouldn't drop if you increase the temperature of a substance, keeping other things constant. But our temperature didn't double, right? It did not double. It did go up by a factor of 1.3, though. And so the pressure went up by a factor of 1.3. Okay, good. So now the way you would do this is you convert these two temperatures to Kelvin, and then take their ratio and then see what the factor is, and it's 1.3. Okay, great, great, great. That was B. Keep track of my slides here. Okay. All right. So let's do this one now. Quantity of ideal gas is contained in a balloon. All right. Initially, the gas temperature is 27 C. We're going to double the pressure in the balloon and change the temperature as the balloon shrinks to 1/4 of its volume. All right, so we got a lot of things changing here, right? Change in pressure, change in temperature, change in volume. All right, so I'm going to give you a good minute for this because there's a lot of things changing here. And now what you could do is also could do a similar thing here. You can kind of reason. You don't necessarily have to get the spot on right number here, but you could simply reason what it would have to be. You can eliminate things, for example. So think about that for a minute. Okay, so let me rearrange the proportionality here. It's going to look sort of like this. So if I rearrange things so I can see what the effects of the I got a little drawing pad here, but I'm not very good at this stuff. Let's see what you had to say though first before I explain this. D, D, B, a lot of B, a lot of D. All right. Well, wait a minute. You can't say that. Hold up. Hold up. Wait a minute. Well, I don't know. All right, so let's see here. We're going to double the pressure of the balloon. We're going to change the temperature so the balloon shrinks to 1/4 of its volume. So what am I doing here? Look, if you look at this, here's what's happening here. This is very obnoxious. T final. So I'm going to double the pressure. So there's a factor of 2 here for this ratio of pressure. And we're going to shrink to 1/4 of volume so that the ratio for volume is going to go to 1/4. And so what we can see here is the temperature will drop by a factor of 2. So we end up with this relationship here. Again, please don't make fun of me. I'm not in... I can write better than this, I swear. All right. Temperature goes down by a factor of 2. Well, that's D, right? Because that's the temperature in Kelvin. So what you would do is you would see this, say, oh, it goes down by a factor of 2. Let's take my 27 Let's convert it to to Kelvin, and that would be 300. Temperature then drops by a factor of 2 to 150 Kelvin. Now you're going to subtract the 275 there, and you end up with a negative temperature, a negative Celsius temperature, though. But you could reason here that, like, okay, based on what's being described here, temperature's going to drop, and D is the only thing that makes sense. Okay, you can rule out the other three pretty darn easily. So anyway, okay. Fantastic. All right. So I think I'm going to do this example here, and then we're going to take a break. Yes, we are. Ugh. I got a headache. I never get headaches. It's weird. All right. Let's look at this example. Okay, what's going on here? We got automobile engine, mixture of air, vaporized gas leads compressed in the cylinders have to be ignited. Typical engine has a compression ratio of 9 to 1. What that means is the ratio of volumes are 9 to 1. Okay. So when you compress it, the volume goes down by a factor of 9. Okay. So we know what's going on with volume. You don't need to know the amount of volume, right? All you got to do is know how much it's changed by. If the quantity of gas is constant, I hope so. That would be a very good engine. What is the final temperature of the compressed gas? If its initial temperature is 27 C and the initial and final pressures are 1 and 21.7 atmospheres. So the pressure, so during the compression, the volume drops by a factor of 9, right? The pressure goes up by a factor of 21.7. And we want to figure out what happens to this temperature here. So my guess is the temperature probably goes up a lot. Probably. I don't know much about cars, but I'm guessing it goes up a bit. Let's see how this works, though. All right, so here's my relationship right here. All right, PV over T. And I know my ratio for final to initial volume is 1/9, so I can go ahead and throw that in here. I know that my ratio for pressures, the final to the initial, is 21.7, so I throw that in here as well. I put in what my room temperature kind of thing is in here, so this is 27, and I have to add in the 273 to convert to Kelvin. And I punch all this out, I get 723 Kelvin, which if I want to convert to Celsius, just because, one thing that's nice to do is if you're given Celsius in a problem, it's generally polite to return the same unit. Okay, it's like a little physics etiquette in a way. Yeah, you return what you're given. So 450 Celsius, which is that's pretty hot, huh? Okay, so here's what we are going to do. We're going to take a 10-minute break. All right, right now. What I would like you to do, though, it's not a hard problem, but I'm going to want you to work out this thing here. If you've had chemistry, this is maybe something you've done, and you may actually know the answer off the top of your head, depending on how much you like chemistry, how much chemistry you've had. But STP is standard temperature and pressure, which is 0 Celsius, 1 atmosphere. And if you have exactly a mole of a substance at 0 Celsius and 1 atmosphere, what would the volume of a container be? So, so you can work that out. Okay, well, I have no idea if that was 10 minutes or not. Let's just say it was. Let's get to the problem here. Well, it's about as easy as it gets. So, but we got mole. We got 8.31 joules per mole per Kelvin. We got our temperature to be 273. And we have atmospheric pressure in here. So we got all SI stuff. This is going to punch out 0.0224 cubic meters But let's do liters there. Remember, the conversion is you're going to multiply by 1,000 basically to get to the liters. 22.4 liters. Yeah, if you have 22.4 liters, that's your container. You got a mole of that gas. You got your temperature to be 0 C. You're going to have atmospheric pressure. Okay. Fantastic. Let's keep going. Now, we are talking about ideal gas law stuff, right? And when it comes to ideal gas law stuff, it is a approximation, a very good approximation, actually. But there's a couple things that you can add to your ideal gas law equation to make it a little bit more realistic. And that's called the van der Waals equation. And we're not really going to do much with this personally. I mean, in chemistry, you'll deal with van der Waals equations. We don't really do that in physics, though, because the approximations are so pathetic, really, that it's pointless. We have better treatments than you know. And what van der Waals equations is basically this: the effective volume of a container is a little bit less than for an ideal gas law, because I mean, molecules have volume, right? And so this factor here, NB, the N here is number of moles, and the B is a statistical factor depending on what the molecule is like. And so that does effectively reduce the overall volume of where the gas can exist in. So there's a factor there. And then additionally, the pressure can be a little bit bigger than what we would expect because of attractive forces that are exerted on they're exerted between molecules. And so again, this is a number of moles, volume, and then A is a statistical factor here that modifies slightly the pressure because you have interactions between molecules now. And so that can actually effectively raise the pressure a little bit because of the attractive nature of those forces. So, all right. But that's pretty much all I'm going to do with this. We have enough to worry about in the ideal gas law that we don't need to incorporate this stuff here. And it's, all right. So, now, one thing that you're going to see quite a bit of in this course on thermo are PV diagrams. Because it's a picture, and a picture can tell us a lot more of what's going on with our system here. And, you know, there's a couple assumptions we make in PV diagrams. A PV diagram means this. It's a diagram that plots pressure versus volume. Volume is on the horizontal axis, pressure is on the vertical axis. And we typically have situations where we don't mess with the amount of gas. So the amount of gas is constant. And so if you have that, then you have basically a bunch of functions that are 1 over x. That's basically what we're looking at here is a bunch of 1 over x functions. And one of the variables in the numerator, so imagine it's like the function's actually like a over x, where a is a constant. But in that A would be temperature, that you know. So if you alter the temperature, you get different what we call isotherms. So if we keep the temperature at a particular spot here and we alter volume or pressure, we're going to travel along this line here. If we increase the temperature, we end up on a different isotherm. There's a lot of ways you can organize these diagrams, but the standard convention is to have pressure and volume plotted, and then you can vary temperature and you create different 1 over x graphs. And with 1 over x graph, if you change the numerator, constant numerator, I mean, what happens is you have just a greater amount of pressure for a given value of x. So the whole thing just kind of goes up in the diagram. And so if you're looking at a bunch of isotherms, it's very easy to figure out what's a higher temperature, what's a lower temperature. And if you transfer, if you move around on here, which we're going to see a lot of, when we look at a lot of thermodynamic processes, where say we have an isobaric process, so we don't change our pressure at all, okay? And then we decide to say increase the volume, okay? We go from one isotherm to another one, and that means the temperature is going to go up in a situation like that if we kept pressure the same. Or we could drop down here. Constant volume, right? Constant volume process, which is going straight down here. The pressure drops, and then we go from an isotherm that's higher up to one that's further down, and so we can see there that the temperature changes. So movement on a PV diagram can put you on different isotherms, right? All right, good. Get a lot of practice with this. Don't you worry. All right. This is a PV diagram. It shows 3 different possible states for a certain amount of an ideal gas. Which state is at the highest temperature? So we have 3 different states there. Which one is at the highest temperature? See a letter in the chat. Ugh, I don't feel so good actually. I got a headache, stomach hurts. Oh, it didn't help that I haven't eaten anything today. That's kind of a dumb move. Right. C? Are you kidding me, people? C? What? C's right. C is right. Some of you just get it wrong on purpose, so we have something to talk about. Don't keep getting things right all the time. No, that's great. I'm glad. I'm great. Just doesn't make it interesting if everything's easy, you know. F, come on, R. All right, I appreciate that. You guys with the Z's out there, thanks for hustling for us here. All right, guess what? This is why. Oh my goodness, calm down now. Don't get wild. Now you're going to throw 2 letters out there, then there's going to be random words. Can't deal with that right now. All right, here is one potential isotherm. Okay, now if you look at the position of all these, there's no way you can intersect these isotherms. So having 3 being directly above 2, there's no possible way you can intersect. 1 being lower and to the left, there's no possible way you could intersect. So these are exclusive states. Okay, so they're all different temperatures, but 3 is the highest temperature. Okay, there will be ambiguity if, for example, there's a point like over here. I mean, could that be on the same isotherm? Yeah, it could definitely be on the same isotherm. Okay, if you throw this 0.3 a little bit to the left here, oh yeah, you could end up with the same one, but always moving up and right, up and right. There's no ambiguity there. All right. Uh-oh. Stuff too easy, people. I can teach in a different language if you want. That'll make it harder, right? I'll think about it. I don't know any other languages, so it may be more work for me to do that. But I got Google Translate. I'll figure it out. All right, now this here is non-ideal gases. It's a little tricky for these. In particular, we're looking at critical temperatures. And this is when we have phase transitions. Now, we don't want to do phase transitions because guess what? You got a phase transition, your ideal gas becomes, not a gas and not ideal or anything. So, but what happens is the temperature starts to get lower. We do need to be cognizant of the fact that we could enter phase transitions. And that's a tricky thing You know, everything could be going fine in our problems. We have a bunch of gases here, and then we're not really, you know, we're saying like, you know, 211's easy. I'm not gonna worry about this stuff. And then all of a sudden I throw a problem at you where the temperature drops and there's condensation. And how would you know that? You wouldn't, unless you looked up your substance and you checked something. This is true in the calorimetry problems that we have. You know, if heat's getting thrown around left and right, and you know, things are heating up or cooling down or whatever, you got to be mindful. Look at all your substances, and look at their melting points and boiling points, and you got to ask yourself, am I running into a problem here? Okay, if we lower the temperature enough here, we reach the critical point, and then we don't have an ideal gas law anymore. In fact, what happens, we have this weird transition here where we're a liquid for a little while, and then if you drop the, you know, well, I guess this is increasing the volume here in this case here, but you could also do it with pressure as well. You could enter back into a gas state. So my whole point for this is just you got to be mindful of temperatures, and if something drops a lot, you do need to think in the back of your head, like, well, is it possible there's condensation here? And if there is, well, I guess it depends on the problem. Either it's just you know, you realize that this condensation is like this problem can't be solved, which is certainly possible. Or there is condensation problems we have where you can deal with them, like if there's specific energy or problems, something like that. Okay, anyway. So just watch out. All right, now this is gonna get good. This is gonna get real good. All right. So we want to look more carefully at what it means for a gas to have pressure. Right? That's the idea. And when we say a gas has pressure, remember the definition of pressure, right? Let's get into this. Okay, I'm gonna try to draw here, and again, my 4-year-old's not drawn. It really is me. So just be nice. Okay. So pressure. Oh, maybe I have to hit annotate. Maybe I should let my 4-year-old do this. It might turn out better, to be honest. And I messed up the screen share somehow. Lovely. Or maybe I didn't. I don't know. What's going on here? Okay. So what's pressure? Pressure is force over area, right? Well, what force? Well, the force is the collisions that are taking place with the molecules and the walls of the container. Okay? So ultimately, that's what we're looking at here. And when we say something has pressure, because there are enormous number of molecules making collisions with the walls of the container. And those frequent collisions are experiencing impulses. You remember that from 110, impulse, force delivered over time. And you know, we're going to try to relate the microscopic collisions with what's going on macroscopically. Okay, so here's how we're going to look at that. If you look down here at this particle that's about to come in collision with the wall, the way we can relate this in terms of forces will be this. We're going to say, and where's my thing here? Okay, way down here. So what we're going to say here is that the object is going to experience a change in its momentum. So that's the change in the x momentum, and that's given by, again, we're going to assume this is a perfectly elastic collision, and it's going to be 2 times m times the velocity in the x direction. Now, why is there a 2 there? Well, okay, remember what change in momentum is. It's final velocity minus the initial velocity. Okay, well, if they're the same going in and coming out, which they are for elastic collisions, then your difference is simply 2 times your velocity. So our change of momentum here is simply 2m delta x. Okay, now, and then you hopefully will also remember that force, I'll write this down here, is dp dt. So I can come over here and simply divide this by a dt, not dt, I'll do a delta t here. And that is a statement of average force. Okay, and that's the statement that we have right over here. You multiply that by the number of collisions that are taking place, which is effectively, you can say that in a given amount of time, every single molecule is going to bounce off the walls at some point. And so you can throw in a capital N here to correspond to a number of collisions that are taking place. And so this is one way you could talk about the force that's exerted on the wall overall. Okay, it's sort of an average because you have an average speed here. Not every particle is going to be moving at speed x, right? So we'll talk about an average there. All right, so let's move on from that. In fact, let's see. Well, we can develop this delta t a little bit here. Let's talk about that. So let's say that the box here has a length L to it, okay? So the A that I'm referring to, this is the area of the collision right here, this L. A given particle is going to travel across here, hit the wall, and then travel back. Okay, and so if you want to talk about an average time between, how much time is going to elapse between a given collision with a wall, it's going to look like this. It's going to be the speed of the particle, Vx, delta t, equals 2L. Why 2L? Because the collision, the particle is going to travel across the box, hit the wall, travel back. Okay? And so in between that collision, it's the particle's traveling back and forth. Right? So that's a 2L that's in there. So I can change this a little bit more, and I'll write an additional step down here. So I'm going to plug in my delta t down here, and I get a 2m, and this becomes Vx squared, because what happens when I divide here, the 2L's in the bottom, and the V comes up to the top. And so I have an expression that looks like this now. And you can cancel the 2's out here. And that's how my force is going to look right now. All right. Now, let's move on, actually. I'm going to move to the next slide. Uh-oh. Come on. All right, so what I'm going to do now is I'm going to take my expression for force, and I'm going to insert that into the definition of pressure, right? Pressure is force over area. So let me write out what that's going to look like. So I'm going to take my expression, and so my force was what? It was m Vx squared over AL. Now the A comes from here, this A. And in fact, I'm going to throw the N in there too, because now we're talking about the overall pressure, so that's going to be number of molecules in there. The bottom here, this stuff right here, the surface area of the container times the length of it, well, that's volume, actually, right? So we can change this into a NVM. All right. Now, the only issue we have with this is that we have a Vx here. Well, what we can do here is we can, the velocity of a given particle is going to have 3 degrees of freedom. It can move in x, it can move in y, it can move in z. So if you'll notice here, there's a 1/3 factor put in here. Simply taken into account, there's 3 degrees of freedom. At any one time, you're going to hit one particular wall, right? So we throw a factor of 1/3 in here, and then we change this speed not just to x, y, or z, but this can be the overall speed, which is what we refer to actually as the RMS speed. And because there's velocities here, if you're going to combine a bunch of velocities together, you're adding up a bunch of squares, and so the way that we're going to most easily model that, because it can be tricky to talk about how you deal with the velocities here, but the easiest way is to basically sum all these up, and you get a factor of 3 right down here, and then this is going to be known as the root mean square, so it's a square root of the square averages. And so now we got this particular expression here. Well, there's only a little bit more we'd have to do, because look, I have a P here, and I got V right here. And so what we're going to do with this is we can rearrange a little bit here. And I'm going to write it a little further down here. So PV is equal to 1/3 NMV squared here. Now this is starting to look a lot like, well, the right side here is part of the ideal gas law, right? And the other side over here looks like a kinetic energy. So what I'm going to do here is I'm going to replace the PV with the equivalent in the ideal gas law. So that's going to be NKB T equals 1/3 NMV squared. The ends drop out. And then, oh, that's a third, sorry. That's a 3. Okay. And then the last step is let's make this thing actually look like a kinetic energy. And so the very last step down here is I'm gonna move the 3 to the other side, and I'm gonna divide it by 2. And then the other side is gonna be mv squared. So what you see on the right-hand side here is the average kinetic energy of our particles, and it's related directly to the temperature of the substance here. And so that's how we ultimately make this connection. We just look at collisions, we work out a force on average, we work out a pressure, we relate that to ideal gas law, and we get this really neat expression down here, which ultimately, when you clean all of that up, you're now dealing with this expression right here. So in the middle is what we just derived, right? We just derived the stuff in the middle here. What you see at the top are different expressions that you can get to calculate the root mean square speed of a molecule. And so that's just rearranging this thing here, and it can come in one or two different forms. It can have the Stefan-Boltzmann law and the temperature in there, or you can convert this, like we said earlier in the class, right? What you can do is you can throw in a Avogadro's number in here, and when you do that, this mass becomes a molar mass, okay? And now, actually, for this case, that would be kilograms per mole in this case here. And then R is your it's the gas constant, right? So both expressions work. It just really depends on what you're given. If you have an individual mass of a molecule, and this is going to have to be a pure gas of some kind. If you don't have a pure gas, you're going to have to figure out an average mass or like an average molar mass. Like if we do air, you got to do that average in there. Now, one more additional thing we could do here is this is an average kinetic energy of the molecules. If we were to take this and multiply this by n, okay, so I'm going to multiply both sides of the equation because this is an average kinetic energy, right? So if I multiply this equation in the middle here by n, number of molecules, then n shows up here. Okay, and again, to go back and forth between the different versions of the ideal gas law, you have n. Why did that turn red all of a sudden? NKB equals NR. So I can multiply both sides by n, and then I take the NK. They don't show the subscript B, but any K you see here is the same. So it's this Boltzmann constant. We swap it with NR, and now we create this expression at the bottom, which is pretty dang cool if you ask me. Oh. Okay, see, I'm gonna call my 4-year-old over because I clearly can't do this, and I can't clear it. Why can't I clear it? I angered somebody. I clearly angered somebody. Why can't I erase? I don't even know what's going on anymore, people. Anyway, this one down here. Wait, that's so weird. I guess PowerPoint is deciding to take over here. Anyway, this expression down here becomes the overall energy. It's the total kinetic energy of all the moles in the gas there. It's the total number of energy, total amount of energy. So this is, wait, what? Ignore this. I don't know what this is. Sorry. It shouldn't say average. On average. Not average. It's the total. In fact, way back in Physics 110 and periodically throughout, we've always talked about the thermal energy of the system. The thermal energy of the system is always this mysterious thing. Well, guess what? That's the thermal energy of the system. There's the actual physics behind it. When we talk about putting heat into a substance, taking heat out, it's that quantity that we're messing with. So if you have a substance, you have a bunch of water, a number of moles at a given temperature, right? And I say we're going to be taking out 1,000 joules of energy. Okay, well, you work out this number here, subtract out 1,000 joules, and you can see how much leftover heat you have, and then you can convert that to another temperature. Doing calorimetry stuff, you know. So all these equations, a lot of equations here, a lot of things going on. But let's do some examples. Okay, I gotta make sure to not save this. All right, so we got a rigid container, holds both hydrogen gas and nitrogen gas at 100 C. Which statement describes their RMS speeds? So what's moving faster? So there's a nice concept here, but there's also a mathematical reason in here as well. So let me know what you think. Got a lot of shy people in here. C's, great. Okay, so the concept is this. I mean, hydrogen weighs less, right? That's it. Hydrogen weighs less. So you should expect it to go faster for a given temperature. But mathematically, what's up? Let's go back. Mathematically speaking, you're looking at well, either one of these is fine, but I mean, I like to use the molar mass stuff myself. But the molar mass of nitrogen is higher, right? Molar mass of nitrogen is 28. Hydrogen gas is diatomic. It's 2. Factor of 14. What's the square root of 14? Square root of 14 is 3.74. So on average, and I use that very loosely because root mean square is not exactly an average, but it's very close to an average. I'm just going to loosely say it, but I'll just say root mean square. Root mean square's speed of hydrogen is going to be about a factor of almost 4 larger, which, you know, I mean, when you look at our atmosphere here, right? Nitrogen, oxygen, they're stuck here, right? What about things like helium? What about things like light gases, methane, ammonia, hydrogen? You look out at Jupiter, right? It's got tons of that stuff. Okay, Saturn, tons of hydrogen, tons of helium. Why? Well, because at the temperature that we are at in the solar system, the root mean square speeds are high enough that in many cases they can exceed, or at least their distribution of speeds can exceed the escape velocity. And so they're gone. So that's how we study atmospheres, at least in astronomy. We look at temperatures, we look at the constituent gases, and we look at what the distribution of speeds are, and then from that, you do a little statistical analysis. You can figure out like a loss rate. How quickly do you lose a gas based on the distribution of speeds? Ooh, that's fun stuff, tell you that. All right, so a rigid container holds both hydrogen gas and nitrogen gas. Which statement describes the average transitional kinetic energies of the molecules? That was the same question. Oh yeah, they both. I'm not fooling anybody, clearly. B's Right, because the average kinetic energy is a function of one thing, and that's temperature. And if these things are at the same temperature, they have the same average kinetic energy. Okay? The difference is they have different masses, so they have different speeds, but the kinetic energy is the same. Fantastic. All right. What's up? No R's, right? No P's, no betas, nothing like that. Aw, thanks. All right, let's do this problem. We're on the RMS speed of helium atoms. Let's do it. Let's just do it. All right, so helium is a monatomic gas, if you did not know. It's a noble gas, doesn't really like to hang out with itself or others too much. So that's a monatomic gas for you. We want to figure out the RMS speed, so we have two expressions for that, right? We have the 3 kT over m, which is the mass of one molecule, or we have the 3 RT over molar mass. Both will get you the right answer. I guess in this problem I decided to go with the KT version, even though I just was going about how much I love the molar mass version, but I guess I just felt differently whenever I made this slide. I think it was about a year or two ago. So let's work it out. We have 3, we have K, 1.38 times 10 to the minus 23rd. We got our temperature, which is 60, but we got to add the 273 to get it to 333, so that's in here. And then helium has 2 protons and 2 protons and 2 neutrons normally. When I say normally, I'm like very normally. There really isn't any other isotope of hydrogen that you'd find. I mean, like periodic table, where like my periodic table here. Yeah, the mass of helium is the mass number is 4.0026. So I guess there's some helium-5s out there. A little bit of helium-5s hanging around somewhere, or helium-6s, I suppose, but it's probably not a helium-6. Anyway, so 4 times the mass atomic number. And then we do all this, we get our speed of 1.44 times 10 to the third, which may sound crazy, but that is the root mean square speed. 1.4 kilometers a second. You think, what the heck? 1.4 kilometers a second? Well, guess what? We're going to work this out later. Not today, but you could work out a mean collisional rate, which I don't think we do today. We're going to do that on Wednesday. And you will see that it's not like there are air molecules like flying around at a kilometer per second in your room. I mean, they are, but they move that speed for like a fraction of a second, a really short period of time, and then before they undergo a collision. So this collision's all over the place. And it's one little molecule, so it's not going to hurt you or anything like that. But it makes me surprised. But yeah, for most gases, they are moving like a kilometer per second around. But the average time between collisions is like tiny. Really, really, really small. Okay. Anyway, that's why you look at that. Because the first thing I would say, if that was you, I'd look at that and be like, what? Kilometer per second? Get out of here. Stop joking with me. All right. So I got a few more slides here, and we're going to be done. We still got 20 minutes, though. All right, we're good on time, I guess. All right, so we got 2 specimens of an ideal gas at the same temperature. Great. Specimen 1 has the same total mass as specimen 2. That's nice. But the molecules in specimen 1 have a greater molar mass. Okay, so that means the number of moles are different, apparently. All right. So, yeah, so if we have the same mass, that's fine. But the molar mass is different. That means the number of molecules apparently is different. So which specimen is the total translational kinetic energy of the gas, of the entire gas, greater? Okay, so the idea here is you got to think about what actually has more moles, right? More moles. B, 13. Cool. All right. Answer is B. What's going on here? Same mass, right? Same mass, but if you have a greater molar mass, right? Number 1 has a greater molar mass. So that means you don't have as many molecules there, you don't have as many moles. Specimen 2 has more moles, right? So same mass, got to have more moles, and the total kinetic energy is a function of the number of moles and the temperature. So apparently specimen 2 has a greater amount of total kinetic energy. Now, molecules in specimen 1 have a greater molar mass. That means the average speed is going to be lower for those, right? So 2's faster and greater amount of energy. Fantastic. All right, it's a lot of things to worry about here. All right, what is the average translational kinetic energy of an ideal gas molecule at 27C? What's the total random translational kinetic energy of molecules in 1 mole of this gas? All right, trust me, it won't always be this easy. I'm just warning you. It won't always be this easy. All right, we got 2 expressions for this stuff. The average kinetic energy, 3/2 kT. Okay? The total amount of kinetic energy, 3/2 nRT. Okay? So these are very different expressions. One contains the amount of substance. The other one does not contain an amount of substance. That's the big difference between them. An individual molecule, whatever this molecule is, we don't need to know what this molecule is because there's nothing about these equations that asks us to identify the molecule. We don't need to know that. Okay, 27C is a convenient number because that's 300 Kelvin multiplied by the Boltzmann constant multiplied by the 3/2. We get 6.21 times 10 to the minus 21 joules. That's adorable. A little tiny bit of kinetic energy. All right, but then when it's with all its friends, all right, we got a whole mole of these things. So what if you got an entire mole of this stuff, right? So what I'm going to do here is it's going to be 3/2 times 1 mole times 8.31. That's the gas constant, right? Times the temperature. That works too. 3,740 joules. It's not too bad, all right? Now, there's an easy way to do this problem in a way, right? I mean, did I have to use this right here? No, I did not. Because guess what? If one particle on average has this energy, I can just multiply this by Avogadro's number. And then you get the same number down here. But I don't want you to do that. I mean, I guess if you know how to do that, then you probably already know how to do a lot of things in the class already, I guess. So do whatever you want to do. But this is more direct. Direct in terms of the concept. But yeah, you could simply, the difference between these two is Avogadro's number, that's it. So, now, let me give you more of a realistic picture. Now, we're not doing this in this particular class, but this is an average. And we glossed over one detail here. And that detail is talking about the speeds of the objects. We introduced the root mean square speed. There's a lot of differences. There's a root mean square speed. There's an actual average speed. And there's another concept that we're going to talk about later. I can't remember what that is off the top of my head. It was some other speed. There's like 3 different speeds we can discuss here. But the reality is that, you know, while we can talk about averages, and that's fine, not every particle will be traveling at an average speed. And there is a distribution of speeds. And that's really where the concepts of statistical mechanics come about. But it's complicated. One of the reasons why it's complicated is because to some extent you have to start devoting a lot of time to quantum mechanics. To figure out those speed distributions is not simple. In fact, one of the very first principles, well, basically the first principle that quantum mechanics was designed to solve was to understand why objects glow when they're hot. That's really it. Why do objects glow when they're hot? at the turn of the last century, going into the 1900s, we didn't have a really good sense of why that was. And in fact, we'll discuss this at some point. I don't know when we discuss this. It's like way near the end of the class, but they couldn't model it appropriately. And then when they incorporated the new quantum mechanical treatments to things along with some statistical mechanics, then everything works out nicely. But the reality is there's a distribution of speeds. And we will look at that a little bit. I'm not telling you we're not going to do that at all. In fact, I think next class we actually take a look at it. But we're nowhere close to being able to tackle that mathematically at all. So, anyway, I think we got one more example, and we're going to be done here. This is meant as an in-class, but we're wrapping this up right now. So let's just get into it. What is the total translational kinetic energy of the molecules in 1 mole of gas at STP? Well, we know what STP is, right? It's at 273 Kelvin. There's really nothing else about STP that we need for this because we don't need pressure. We don't really need anything. And if we put the numbers here, 3/2 times 1 mole times the gas constant times temperature, we get our 3,400 joules of energy in that gas. Not a ton, but then again, gas is sparse. Right? No big deal. Okay, let me stop my video.